The climate change in the Cape Fear region. Is that what everyone is seeing right now? Okay, excellent. Yeah, I'm Tim Armstrong with the National Weather Service. I'm a meteorologist, but also the climate program leader here at the Weather Service, which means that in addition to forecasts and warnings and so forth, I'm also responsible for collecting, quality controlling, and archiving climate data across southeastern North Carolina. In Wilmington, we have a really amazing history of climate data that goes back to the year 1871. It's the longest continuous period of climate data for any station in North Carolina. So for us here in the port city, we've got something else to be proud of there besides just our beautiful city. But for today's presentation, we're going to talk about, first of all, the difference between weather and climate. We hear those two terms used interchangeably sometimes, but they do have slightly different meanings. We're going to look at climate change over Earth's history, going back to the last ice age and up to the present, and the causes for some of those big changes that have occurred. We'll look at more recent climate change, zooming in just to the Cape Fear area here to Wilmington. We'll look at our local observations that we've collected here in Wilmington over the past 140 years, and also the causes for the changes we have observed. And then we get into future climate change, what's going to be happening as we close out this century and move into the next. What's the magnitude of climate change going to be, and what could some of those impacts on society be as well? So we'll start right off here with weather versus climate. Well, there's a really nice little saying. It sounds like something Mark Twain would have said, but I can't verify it was him. But the saying says, climate is what you expect and weather is what you get. And basically, weather is the current state of the atmosphere. It includes things like when you look out your window, you see the clouds, you see the wind outside, you can measure the temperature on a thermometer, you can measure the rain with your rain gauge. What's happening right now is weather, essentially. And if we average weather out over a long period of time, we get climate, which is the observed weather over a very long period of time. Now, I've got this sliding scale there that goes from hours on the left end out to centuries on the right end there of different weather and climate events. Things like thunderstorms are going to, and sea breezes. These are things that happen and just last an hour or two or three at a time, and then they're gone. Those are certainly going to be weather phenomenon. On the far right end of things there, we see climate and climate change. Those are things that take place over decades and centuries. So in between, we have where these two scales sort of merge together there, and you sort of get an idea of the various things we would call weather and climate. The cutoff point generally is in the months to years phase there. We think of El Nino and La Nina, that's a 2 to 7 year cycle, as sort of that midpoint between a weather event and a climate event. So that's the difference there between weather and climate, short-term versus long-term occurrences in the Earth's atmosphere. Now in NOAA, that's the National Oceanic and Atmospheric Administration, that's the parent agency of the National Weather Service, we've agreed to use a 30-year averaging period to compute normal. So we need at least 30 years of data from a point before we can start figuring out what that local climate is at that point there. And literally anything you can measure, whether it's temperature or rainfall or the number of lightning strikes you get or river levels, these can all be looked at from a climatological standpoint there. And the graph I've got displayed is our annual rainfall for Wilmington going back to the 1870s when we first have data. And each little dot on there indicates each year's annual rainfall. And then the thick, bold blue line across there is a moving average showing how our rainfall over the past 100 years has generally been increasing. And that's one way we can look at climate history to see how the climate is changing and where things might point to in the future. And you'll notice here just recently, just before 2020, in fact, the year 2018, you'll see that one point sitting all up there by itself. That was the year Hurricane Florence struck us. And we measured over 102 inches of rain that year, by far the most ever in Wilmington. So even after 100 years, you can still be surprised by some of the things that the climate can throw at you there. The climate has changed, obviously, very dramatically over Earth's history. There's a webcomic called XKCD. Some of you may have stumbled across on the internet before. It's one of my favorite. I go to several times a week. And he published a graphic indicating how thick the ice sheets were at various locations about 21,000 years ago. That's the peak of the last major ice age. If you were going to Boston to see a Red Sox game 21,000 years ago, you would have had to dig through over 4,000 feet of ice to reach ground level. This is when the ice sheets covered a good portion of North America from the poles all the way down to the northern United States. And you can see at various locations there how thick the ice caps were believed to have been at those locations. Now this ice, obviously, the water came from the ocean. So ocean levels were much, much lower 21,000 years ago compared to today. all the water that's in the ocean was sitting up on land in these great ice sheets. As that quickly melted off, it led to a lot of changes besides just rising sea levels. The weight of that ice being relieved from the ground actually has allowed the ground to rise across much of Canada and the northern United States. And that ground is still rebounding today as the weight of all that ice came off of it there. So if we look at what we believe temperatures may have looked like when those ice sheets occurred, this is a reconstruction. Pardon me just a minute. Get some water there. This is a reconstruction of what we believe surface air temperatures were compared to today during the last glacial maximum. And you can see over central Canada, 20 degrees Celsius or more, that's almost 40 degrees Fahrenheit, colder temperatures on average than what we measure there today. That's obviously because the ice is no longer there and you're able to get sun to the surface to warm the surface up, produce much warmer weather and climate than what was experienced back then. But it's interesting that some parts of the world, the tropics, for example, very little difference compared to what was experienced then to today. So obviously the ice ages had much more of an impact where the ice actually occurred. If we look at that in a graphical form, and this is a reconstruction based off of a lot of different data here from coral growth rings in the shallow oceans, from looking at different isotopes of oxygen in the ice and water, we can theorize what the temperatures would have been like at various points throughout history. And you can see Earth's global temperature between 3 and 4 degrees Celsius colder during the ice age, but then rapidly warmed up over 10,000 years to reach levels fairly similar to what we have today. In fact, about 8,000 years ago, the temperatures were actually very similar to what we had in the 1950s, and we're actually falling off until there at the very end, you see a spike upward. Now, why did these changes occur? Well, there was a Serbian scientist lived back in the late 1800s by the name of Milankovitch, and he was the first using the astronomy and the mathematics that were developed at the time to figure out that the Earth's axis does not always point at the same tilt relative to the sun that it does today. In fact, he discovered that it tilts over a range of about 2.5 degrees, from 24.5 degrees at its most inclined to 22 degrees at its least inclined. Doesn't seem like a very big deal there. What could that possibly have done? Well, when the Earth's axis is at its maximum tilt, 24.5 degrees, the North Pole during its summer picks up a little bit more sunshine than it does today. That few percent of extra sunshine is enough to ensure that most of the ice and snow melts off. And so there's no way you can really have large or spreading ice caps during that cycle. Now, at the bottom part of the screen there, when the Earth is in the opposite part of its cycle with a smaller 22-degree tilt, now the North Pole region in summer does not receive quite as much energy from the sun. It's now more likely that your ice and your snow can survive the summer up there and accumulate year after year, growing deeper and deeper and covering more area. That ice reflects sunlight away, cooling the climate there. And so over hundreds and then thousands of years, you can create ice sheets and throw the world's climate back into an ice age again. Now, Milankovitch was correct that this 41-year cycle here does occur, and it does have impacts on how much snow and ice accumulates at the poles in both the North and the South Pole. What he did not know at the time, though, is that there are at least 4, perhaps more other cycles that are just as important. And so we don't have ice ages every 41,000 years like he had originally surmised. It seems to be more of a 100,000-year cycle. But the point he was the first to see there, he was correct, that there are naturally occurring changes in the Earth's orbit around the sun, that its axial tilt that do influence the Earth's climate. So back to this graph we looked at here earlier, you'll notice at the very, very end of the chart there, where the green line turns to purple and starts to rise abruptly. That's where we are right now in our current climate. The Earth's average temperature is rising extremely quickly compared to almost any changes we've seen throughout history, even when we were melting ice off the planet at a great rate. So let's zoom into what was going on here, say in the past 150 years or so. This is very high resolution data taken from a number of thermometers and more recently satellites circling the world here. We're able to see that global temperatures have been on pretty much a steadily increasing trend for at least the past 100 years. We know that the year 2020, that's just last year, is now tied for 2016 for the warmest global air temperature measured in modern times. But we also know that the last 7 years, going back to 2014, are also the 7 warmest years ever measured in recent Earth's history. So something obviously is changing here that is causing changes that are not related to an orbital cycle, to the Earth's tilt or so forth. There's something else going on, and we believe what's going on is a enhancement of the greenhouse effect produced by humanity. The greenhouse effect, we should be glad that it exists in the first place. That basically is that gases in the Earth's atmosphere, carbon dioxide, water vapor, methane, there are other gases as well, will trap a portion of the Earth's or the sun's heat, not letting it escape into space and keeping the Earth's atmosphere warmer than it otherwise would be. If there was no greenhouse effect at all, the average temperature of planet Earth would be around 0 degrees Fahrenheit. And as much as we might enjoy playing in the snow, I don't think that's a planet we would like to live on very well. Because of the greenhouse effect, the average temperature of the planet is about 59 degrees Fahrenheit, but it has changed significantly here over the past 100 years, as we've seen in the previous chart. Now, the greenhouse effect has been enhanced here basically just in the past 150 years. And if you think about, well, what would have happened 150 years ago, maybe to cause these gas concentrations to change in the atmosphere, it was the start of the Industrial Revolution, when humanity learned that there are great energy reserves buried underground, coal, oil, and natural gas. We can pull those energy sources out of the ground, burn them, and collect the energy to do all sorts of amazing things. Well, that's been great for humanity, but it has allowed these gases to be trapped in the atmosphere in increasing concentrations. Carbon dioxide that was steady between 250 and 300 parts per million for hundreds of years there. The concentrations have actually spiked over 400 parts per million. And I just looked up the latest data this morning from the NOAA monitoring stations in Hawaii. The latest number this morning was 413 parts per million, so a little higher than what's shown on the chart there. And it actually peaked at 420 back in the spring. The reason it's fallen a little bit since spring is with all the land in North America, the plants waking up during spring and summer, they actually suck a small portion of that carbon dioxide gas out of the atmosphere. So we see a annual variation up and down based on basically, is the Northern Hemisphere in winter or is it in summer? We see a 7 to 8 parts per million variation just based on what the plants are doing at the time. But other gases such as methane, that's natural gas, nitrous oxide, which is a byproduct of producing fertilizer and so forth. All these gases that trap heat in the atmosphere, the concentrations have been rising extremely quickly over the past 150 years. And we can do laboratory experiments that show us exactly how much these gases trap heat in the atmosphere. And relative to carbon dioxide, we see that methane is 23 times more effective at trapping heat. Nitrous oxide is about 300 more times per molecule, 300 more times more effective at trapping heat than carbon dioxide is. So a lot of interesting things going on, changes in atmospheric chemistry that we believe are behind the recent rising temperatures that we're seeing across planet Earth. Now, I mentioned in Wilmington, we have a great weather history here that goes back to the 1870s, longer than any station in North Carolina. We actually have the original books here in our office that were handwritten back in the 1870s up through the 1980s. It then became an electronic record that was kept. But it's fascinating to look back through these old documents here. Thankfully, they've all been digitized now, so we don't have to go back and look at the originals anymore, but the information in there is still very useful to us today to determine what the climate has been doing. So right here in Wilmington, using the data that we collect, this is what it looks like for average temperatures in Wilmington, starting in the year 1875 and running to last year, 2020, the last year we have complete data for. We see that the years 1990, 2019, and 2020 are the 3 hottest years in Wilmington's history here. That's using data that has been collected right here by National Weather Service meteorologists. We see that over the past 150 years, our climate has warmed by about 2 degrees Fahrenheit. And we've noticed the largest temperature increases have been with overnight low temperatures, with a smaller increase noticed in afternoon high temperatures. And at night, when the sun is not shining, it's up to those trace gases in the atmosphere, your carbon dioxide, your methane, your nitrous oxide, your water vapor. Those are the gases that become very important in determining your nighttime temperature. As they've increased, as those gas concentrations have increased, we've seen those nighttime temperatures increase faster than your daytime temperatures. At the bottom of the screen, we see our Wilmington rainfall totals. That's every year's rainfall total back to 1871. They actually had a rain gauge here before they had a thermometer. So a little bit more data there. But again, we see that that average has been gradually increasing over the years. If we go way on back to the year 1920, Our 30-year average rainfall was just a little over 40 inches. It has now reached 60 inches. 60.14 is our latest 30 years rainfall average. That's the highest on record for Wilmington. Of course, that was helped out a lot by 2018, the year that Hurricane Florence hit the area. And this is actually expected to continue into the future. So I want to show you another way we can look at how our temperatures have been changing in Wilmington. This is two different charts here taken from two different time periods, but both for Wilmington. This is looking at summer high temperatures. How are they distributed during summer seasons? The blue graph you see there looks at the period 1891 through 1920. And that was a relatively cool period in Wilmington's history. During the summer, our average high temperature then was about 86 degrees. And you can see that on the right side of that blue chart, it would rarely get into the upper 90s, maybe close to 100 degrees. But certainly it rarely ever reached 100 degrees or higher back then. The red chart now is the last 10 years, which has been a very warm period in Wilmington's history. You can see that our average has warmed up. Instead of our average high temperature in the summer being 86, it's now warmed up to 89 degrees. But notice also, if you look at the 95-degree line on the chart there, where before 95 degrees happened about 1.5% of the time, it's now happening 4% of the time. If we look at 100-degree readings, 100 years ago, you would get a 100-degree reading only about 0.1% of the time. And now we're seeing it 1% of the time. So no one really cares what your average temperature is. That's not the things that affect humanity or the plants or the animals that live around us. It's those extremes. And as the climate has warmed, those extremes, your 95 and your 100-degree temperatures have become much more common. For 95 degrees, we're now about 2.5 times more likely to see a 95-degree day than we did 100 years ago. For 100-degree temperatures in Wilmington, we're now 10 times more likely to see that than we were 100 years ago. Now, if we extrapolate this out in the future, if climate change continues to advance in the same direction, temperatures that we can't even conceive of seeing, say 105, 106, that's never happened in Wilmington, that chart will continue to shift right. And things like that may develop and become a real possibility. You got to think about what's our infrastructure like in Wilmington. What's the Cape Fear Memorial Bridge going to look like at 106 degrees? Are the expansion joints built to handle that kind of heat? What's our power grid going to do? Can it handle everyone's air conditioner running nonstop all day and all night to handle 106-degree air temperatures? These are questions that our society needs to look at closely as we plan for the future, since it does look like the future is toward warmer temperatures, not just here in Wilmington, but around most of the planet. Now, a lot of these projections for the future are made by a group called the Intergovernmental Panel on Climate Change. For me personally, here working at the National Weather Service, my expertise is on today's weather out through about 7 days. So I'm going to turn to the experts here, the climatologists whose expertise is on studying what the weather might be like 30 or 70 or 100 years in the future. And this is, they send the reports through the United Nations. This is a collection of scientists from North America, from Europe, from Asia, from all around the world that get together, write reports every 4 years. And their latest report, this is from the 2018 version of the report here, focused on the southeastern United States, shows that by the year 2070, so we're looking, reasonably far out in the future, but not too far out to plan for, that in southeastern North Carolina, we can expect about a 3.5 to 4 degree Fahrenheit increase in annual temperatures. That's going to raise our average annual temperature from 65 to around 69 degrees. The largest increase is expected to occur in summertime, about a 4.5 degree Fahrenheit increase, with smaller changes expected during the winter and the spring. Now, again, I don't dress differently on a day when it's going to be 3.5 or 4 degrees warmer than I do on a day when it's, a normal temperature. But again, what we're worried about here is what's that going to do to the probability of your extreme events, your 104, 106, 108 degrees, things that really don't happen in Wilmington. What if they do start to happen with any regularity? How are we going to respond? How is the natural systems around us and the man-made systems going to respond to that? One example of that is energy use for air conditioning could rise by 40% across southeastern North Carolina. And that's measured by the increased number of cooling degree days, which is a mathematical construct we use to measure energy usage for heating and cooling. And we're expecting the growing season length, that's the time between your last spring freeze and your first fall freeze, to increase by 15 to 20 days. That's great if you want to get more peppers out of your garden, I guess. But also the number of hot summer nights, that's nights where the air temperature stays 75 degrees or hotter, that should increase from about 25 to 75 nights a year by the year 2100. And I dabble a little bit in backyard gardening myself, and I know that tomatoes do not like hot nights. So there are certainly drawbacks to having a longer growing season and more heat, especially at night. So this is certainly not all rosy situations that are being looked at here. In terms of precipitation, rainfall, our rainfall currently 60-inch average in Wilmington could increase by another 10 to 15%, which would raise our annual average up into the upper 60s, say 66 to 69 inches a year annual rainfall. And again, that doesn't seem like a big increase, but if we look at the extreme events, basically for the southeastern region, how many days a year do we see greater than 6 inches of rainfall? That's probably going to increase by 15 to 20% above what we're enjoying right now. And you think, and we look at the charts there, the largest increase in that is expected during the fall months. It doesn't take a whole lot of deep thinking there to realize, well, what brings us heavy rain during the fall? So that's certainly not some good news there in terms of what we might see here in the Wilmington area. Now, this is the reason we get that heavy rain in fall here. This is just in the past 6 years, 3 of the very devastating tropical storms and hurricanes that have struck the Carolinas and produced extreme flooding. Back in 2015, although we missed out on a lot of this, parts of South Carolina picked up 15 to 25 inches of rain, produced all-time record flooding from just north of Charleston, inland across Sumter into Columbia, South Carolina. Hurricane Matthew, of course, devastated portions of eastern North and South Carolina with anywhere from 15 to 18 inches of rain. We had all-time record flooding along the Waccamaw and the Lumber Rivers during Hurricane Matthew. And then, of course, just recently, we just had the 3-year anniversary of Hurricane Florence that struck this area in September of 2018, dumping rainfall totals over 30 inches in places. And certainly the radar loop there is all ingrained in our minds. We all saw that happen in real time. I'm sure most of us were here in the Wilmington area when that occurred. Now, it's interesting that just a few years before Hurricane Florence, I attended a climate conference with National Weather Service and state climate office officials down in South Carolina. And we were brainstorming, well, sort of what's the highest expected rainfall we could ever conceivably see in the Carolinas from a tropical cyclone. We had seen on the Gulf Coast, say Texas and Louisiana, they've had rainfall totals over 40 inches. We don't quite have the warm water and the very slow storm motion like they do down here. So we knew that probably wasn't a possibility. But we after brainstorming, decided, well, you know, we could see 25, maybe 28 inches of rain out of a storm. Well, then that was right before Matthew came and produced rainfall totals that high. With Florence, we saw a couple of spots over 35 inches of rain. So already the climate is changing faster than even perhaps some of us would have thought was possible there. Now, why are these storms dumping so much heavy rain that maybe didn't occur 50 or 100 years ago? It's the warming of the air that's actually allowing the air to hold more water in it. Think about a cold day, you've got a hot day, you've got a cold drink outside. As that warm, humid air that can hold a lot of moisture in it touches the cold glass, it's forced to dump its water, and that's why you see condensation on the sides of your glass there. That's sort of the same thing with the hurricanes here. The air is now 2 degrees warmer than it used to be. It can hold about 14% more moisture due to that 2-degree air temperature increase. So just by function of the air temperature being warmer, hurricanes can now drop more and more rainfall. We went from 1870 to 1980 without seeing anything more than about 8 or 10 inches of rain out of a hurricane here in eastern North Carolina. In 1984, Hurricane Diana struck. It dumped 18 inches in Southport. Hurricane Floyd then came and dropped over 20 inches in the same areas, and that was in 1999. And now here, just in the past 6 years, we've seen 3 storms that have far, far exceeded anything we saw with Hurricane Floyd. So it does seem that hurricanes will continue to occur in the future, and the biggest impact for us is their rainfall should become heavier and heavier with time. Now, there are other impacts with climate change that we're seeing here that don't just involve air temperatures and rainfall. One is sea level rise. Now, this is from 2 different factors happening at the same time. One is simply the ice sheets over Greenland and over Antarctica melting. As that water flows off land into the ocean, it raises the ocean level. The second factor, which actually is a bigger factor, I think, in some places, is that as the water warms, it literally expands and takes up more space. So the entire depth of the ocean, slowly warming over time, will expand and actually just rise higher along the shoreline than it was before. We've had a tide gauge in downtown Wilmington since the 1920s. And you can see the number of days where we've reached minor coastal flooding. That's 5.5 feet above the mean low water for downtown Wilmington. used to virtually never occur in the 1920s, 1940s, 1960s. Well, just last year, we reached that flood stage 107 times. And under future expectations for rises in temperature and expansion of the ocean levels, by the year 2050, we're expecting coastal flooding, that 5.5-foot mark, to be reached about half the days of the year. By the year 2100, well, virtually every day you're going to get your feet wet on Market Street in downtown Wilmington. Now, again, that's sort of a nuisance thing. I see cars still driving through, a couple inches of water downtown without too many impacts. But what happens the next time a large hurricane comes and we've got water levels that are a foot or two higher than expected? Well, now water is destroying businesses along Water Street. That never really used to happen very often, even with Hurricane Hazel, which was at one point in history the worst flooding ever seen in downtown Wilmington. So the future is really open in terms of how bad coastal flooding could become a concern due to sea level rise and due to these stronger and more frequent hurricanes, which may occur in some sea level or in some climate change scenarios. So a summary of the anticipated local climate change impacts: warmer temperatures for sure. What's going to increase the number of very hot days. We'll see increased human, animal, and plant stress, increased energy usage, mainly for air conditioning. And even if we see an increase in rainfall, when it's not raining, if you can string together 1 or 2 weeks with not a lot of rainfall, the higher temperatures are going to evaporate water faster. And that means an increased drought potential, possibly increased wildfire potential as well. The one silver lining there might be a decrease in the energy used for wintertime heating with warmer temperatures. But that certainly, it seems to me, is any benefits there are going to be outweighed by the negatives seen by your other factors. We're also expecting larger rainfall totals to occur. That's going to increase the amount of flooding we see and also the severity of that flooding. Just mentioned sea level rise. And a last factor, which we're just beginning to study this in some depth, is ocean acidification. Carbon dioxide, when you think about it, is just a gas in the atmosphere, but the oceans absorb a good portion of the carbon dioxide that humanity is releasing. As that CO2 is dissolved in the water, it actually produces a weak acid. Now, we're not talking about battery acid here by any stretch, but it is tilting the pH, basically the alkalinity or the acidity of the ocean water, away from alkaline and more towards acidity. Now, what that does is all the little organisms, from microscopic all the way up to your big clams that fill your entire hand, the shells they make are made of calcium carbonate that dissolves in acidic seawater. So as the oceans become more acidic with time, it could become more and more difficult for some of these base of the food chain sort of little single cell organisms that need those little shells around them to survive. So we could see, and this is going out hundreds of years into the future, we could see some impacts from that, which are not positive as well. So certainly a lot of factors we're looking at as we go forward here due to climate change and its impacts on Wilmington and the Cape Fear region. Now, there are some great resources online, thankfully, if you are new to the topic or you want to see what the latest state of the science is and the state of research for climate change. The North Carolina State Climate Office has a lot of great basic climate change science. There's also a website, climate.gov, that they publish official newsletters and articles showing how NOAA scientists are studying climate change. You also have access to data sets on there that I used showing average temperatures, sea level rise, and so forth. Globalchange.gov is the official United States website. Our input to the IPCC, where you can look at the official reports and outlooks there, including those regional US sector breakouts. And then there's another website there at the bottom that actually shows state-specific climate change projections, where you can drill down to your individual state or a portion of a state and see what the expectations are for the future from climate change. If you happen to think of any other questions later on, there's my email address at the bottom of the screen. I'd be very, very happy to answer any questions or to point you to a resource that might be able to help there. So thank you very much for listening to the presentation today, and I will be available to answer any questions you might have.
Awesome. Thank you so much, Tim. That was very informative. We have one question from Karen. She asked, are hurricanes moving more slowly than they used to so that they park over an area and drop more rain?
That is one of the areas of ongoing research right now. And the latest I heard is that in the mid-latitudes, that means outside of the tropics, so that would include the Carolinas here, the mid-latitudes, hurricanes are moving more slowly. And what that's believed to be a consequence of is we have around the world these large areas of low pressure, like around the equator, the intertropical convergence zone. And then we have areas of high pressure in the subtropics, about 30 degrees north, 30 degrees south. But those areas of high pressure are expanding northward to cover, say, the Carolinas. high pressure has usually very weak winds in it, weak steering currents. So as this occurs, those hurricanes that used to race through the area very fast are moving more slowly. We may have seen that with Hurricane Florence back in 2018. Its forward movement was very, very slow. It rained for 3 continuous days in Wilmington, more or less. If Hurricane Florence had occurred, say, 100 years ago, there's the possibility it would have had a faster motion to it and not have dropped as much rainfall. So that is actually a good observation there. Yes, in the mid latitudes, the hurricanes are moving more slowly. Now, in the tropics, say we're talking about the Caribbean, off the coast of Africa, for example, there's actually been a noticed increase in wind shear that is making it a little harder for those storms to organize there, but also is making them move a little bit faster, perhaps. So it's interesting how climate change is not having uniform impacts across the planet, but it does seem to have some interesting regional changes to it. So thank you for that question.
We have another question. What actions can be taken right now to slow or prevent ocean acidification?
For ocean acidification, it's all about the carbon dioxide. So any way that we can reduce the amount of carbon dioxide we're pumping into the atmosphere will pay big dividends with stopping ocean acidification there. We measure the pH of the ocean water to get an idea how that's changing, and it has come down a couple tenths of a pH value just in the past 100 years, as the oceans are the big sink where a lot of the carbon dioxide we're pumping it into the environment ends up is in the ocean. So anything we can do to reduce carbon dioxide is going to help out a lot with stopping ocean acidification.
So I also have a question. There was a lot of information there that was not particularly optimistic for our future. Is there any research or anything happening that gives you hope or optimism for what our outlook is?
Well, what is optimistic, I guess, at least in the past 5 years, is I found that a lot of the local governments along the southeast coast, and I'm thinking specifically Swansboro, North Carolina, and Charleston, South Carolina, are really taking these messages to heart, and they are working to basically adapt their town's infrastructure, any future building, any refits they do to, say, water pipes or electrical distribution systems. They're taking sea level rise into account. They're taking the idea that rainfall is going to be heavier into account, and they're changing their building codes and changing the look and the lay of their cities to handle that. In downtown Charleston, they're actually in the midst of a multi-billion-dollar, that's B with a billion-dollar, refit of their downtown areas to handle higher sea level. They're getting a lot of just sunny day flooding down there. A high tide during a full or a new moon has been causing trouble for years in downtown Charleston. So they're massively refitting their drainage systems there with one-way valves, raising their streets and sidewalks to try to really help out there a lot. I think as the reality of climate change becomes more and more apparent, you'll see more towns adapting, not just here in the southeastern United States, but around the world, as infrastructure is damaged more and more easily by these storms that might not have caused big impacts 50 or 100 years ago. I'm also really happy to see that carbon-free energy technologies seem to be right on the cusp of a big revolution in terms of generating electricity with solar panels, with wind, methods that don't necessarily release a lot of carbon into the atmosphere. That's possibly a silver bullet that could help mitigate the worst impacts in the future. Now, these IPCC reports will actually have multiple scenarios going forward based on how society responds to climate change. Do we massively curtail the amount of carbon we release in the atmosphere, or do we have business as usual? And there are different impacts that are modeled along those different scenarios there. You probably saw some of those in that graph I showed for downtown Wilmington. We're actually at the worst case right now in terms of how much our flooding is increasing here. So we're certainly on a not so optimistic path, but I would be hopeful in the future that maybe we can take the reality of this into account and make some changes at a large societal level.
Hopefully we will do that. I also had one other question about the Milankovitch cycles. Yes. Are we in a cooling or warming cycle at the moment?
We are actually in a cycle that will promote cooling going forward over about the next 6,000 years. We all learned in school the Earth's axis is tilted 23.5 degrees with respect to the equator. It means on the first day of summer, the sun's rays are directly overhead at 23.5 degrees north, and the first day of our winter, the sun's rays are directly overhead at 23.5 degrees south. That range is actually shrinking very, very slowly, and in about 6,000 years, it should reach its minimum of 22 degrees, and that would be by itself a cooling. Now, some of the research I've read indicates that maybe in 70,000 years or so, we would be naturally entering a new ice age. Well, there's been so much modification of the atmosphere from our activities over the past 150 years, that it's very likely the next 1 or 2 ice ages will be skipped entirely. That even with the shorter or the cooler polar regions due to decreasing sun angles during the summer, which would favor more ice normally, we've changed the atmosphere so much it's going to trap enough heat to offset the next few ice ages.
Wow, that's crazy. It looks like we have another question. Where are we in technological development to remove carbon dioxide from the air?
Well, there was a story I saw just in the last week that in Iceland, I believe, they're doing a pilot project with these large machines where they actually, I'm not sure exactly the details of how it works, but large metal machines that filter air, pulling the carbon dioxide out and storing it deep, deep underground in some of the interesting geology they have under Iceland. That's a pilot project there. I happen to think that nature may have figured this out better than we have in terms of the green trees, the green grass that grows around the planet. It does an excellent job of pulling carbon dioxide out and storing it. So it may be a combination of those factors going forward, a reforestation of the earth and maybe some sort of technological prowess that's able to help there. But in terms of technological development, I think we're just in the very, very early pilot project stages of figuring out how that could be accomplished.
Another hopefully optimistic thing that we can look forward to is increasing that our abilities to do that.
Yes.
All right. Well, I think that is all of the questions that we have. If anybody else thinks of anything, we can send out Tim's email information. It's easily accessible. Thank you so much for joining us today, everyone for joining us, and Tim particularly for putting on this awesome talk. We really appreciate it. And it was very fascinating. And for all of you attendees, we are recording this webinar. So if you want to watch it again later or send it to your friends and family or whoever, we'll get that posted in the next week or so. So thank you all for attending. Thank you, Tim, and everyone have a good afternoon.
Thank you.